But I did promise a talk by the title of Odd Turbulence, and I usually like to start this talk by asking what is odd about it. And once a friend of mine in Paris answered, certainly the people who work on it. But I think there's a bit more to it in a more, in a more mathematical sense. And perhaps a more defining, a good starting point is another question, is almost deceptive in its simplicity, which is, what is viscosity? Okay. So usually when you study media, you will start, for example, simple fluids, you will start with a constitutive relationship, relating stress to velocity strain. So in standard notation, this is velocity in the k direction with gradient in the L direction. You don't even need to symmetrize. And the viscosity coefficient is indeed this rank to this tensor that relate one to the other in a linear fashion. And at least when I studied this stuff in elementary classes, immediately I associated the viscosity intuitively to the presence of dissipation in that media, in a fluid. And if you take this view, which is certainly granted for a simple fluid, then you will indeed view the viscosity somewhat more formally. So power being dissipated means entropy being generated. So power means an entropy generation rate, which I can write Ts dot. And the viscosity then is just this object. This is an equivalent statement to say that the power being dissipated is a quadratic form that you can write like this. Okay.
Just on Zager coefficient.
Yeah. I mean, for a simple fluid on Zager reciprocity relationship, demand this. But please notice a fact that perhaps we take for granted is that this statement immediately implies major symmetries of this object. All right? As Grisha pointed out, this is almost inescapable with a simple fluid. Much more complicated things can happen if you have fluids made, charged particle in the magnetic fields, or other intriguing things that we're going to describe. Why? Because, in fact, what's going to be odd about the subject is that we're going to be considering a class of fluids where this is not true. Mathematically, if we did not impose, for good reason in some cases, on Zager reciprocity relationship for a simple fluid, you could represent any tensor like this as a sum of an even and an odd part. And here is the technical sense in which odd will appear. So the even part, even, will have a plus sign under exchange. Let me use some color. It's helpful in this case. Under some colors, no colors, under exchange of pairs of indices. Okay? So the even picks up a plus. But you could also define an odd component. I'm going to call it odd or O. I'm going to use it interchangeably. The odd one will be associated with a minus. Okay? So odd viscosity means whenever you allow in the viscosity tensor the presence of antisymmetric component or non-symmetric components. Okay? You can probably already see that the presence of this components demands some statement about how you would physically generate them. These terms with an odd, with a minus sign here, as you can see here, even if you rewrite this as a collecting index beta and alpha, you can already see intuitively that the odd components will generate antisymmetric matrices. So they will inevitably have a chirality. So even at the level of a generic symmetry analysis, you can have glimpses of the type of physical systems that will generate this type of beast. So the plan that I have today is to study turbulence in the presence of additional odd viscous coefficient. But before doing that, I would like to give you some sense of where you find in nature odd viscosity. I would argue that, it's not nature perhaps, but if you open Landau-Lifshitz, which is a good approximation to what nature is for a physicist, you will find this in the earlier part, the even, the statement that Grisha was mentioning. But if you keep reading and you go all the way to the part dedicated on plasma physics, you'll hear about something called gyroviscosity, which is exactly what I'm referring to as odd viscosity in this talk. May I use the slides for just a couple of seconds? I mean, experiments are not always best illustrated on a board, rarely, in fact. Yes, we have to lower that. You're right, sorry. I apologize if my mechanics with this are not optimal. So, a class of systems that can display odd viscosity are systems that have generically a violation simultaneously of parity and time reversal symmetry. This you can see also formally. But to give you an idea, let's imagine that you have a fluid, and this fluid is composed of spinning particles, all spinning with respect to, say, the z-axis. Okay? So there is this micro-injection of energy that keeps all the particles going on. And there's got to be a microscopic injection of energy, because if there is normal viscosity, that would be stopping if you didn't keep pumping at the microscopic scale. Now, this can happen in laboratory situations. For example, my friend William Irvin at the University of Chicago took colloids, which are particles of the order of microns. They have in-plane magnetic fields. Sorry, they're in-plane dipoles. William applies an in-plane magnetic field. Let me do it. He rotates it. And by rotating the magnetic field, rotates all the dipoles. So this is a driven colloidal system. In this system, in 2 dimension even, odd viscosity has been measured. Now, I have to say, and these are spinning embryos. Embryos that just spin by themselves, within which both odd viscosity and odd elasticity have been studied. But the study that I want to bring to your attention, because this always happens when they're buried at the beginning of time, or at least what looks to somebody of my age at the beginning of time, there's been actually very precise, some of the best measurement of odd viscosity in 3 dimensions in polyatomic gases, accompanied by beautiful studies in kinetic theory by the British school and the Dutch school of Ben Acker and others. More recently, the topic has been rediscovered. Well, I didn't mean it in a sarcastic way. It's been restudied in quantum system, where additional features emerge in graphene. In graphene, you have electrons in a magnetic field. That's different from particle spinning, but if they go on cyclotron orbits, from a perspective of symmetries and conservation laws, the problems are very similar. So here, there's also a very recent measurement. And I would say this is a somewhat generic phenomenon, okay? Because, as I said, its root cause is fundamentally in symmetry and in breaking symmetry and conservation laws. Now,
out of curiosity, what makes embryos rotate?
yes. Next question. I mean, they all do it, but I mean, Nikta can talk to the embryos. And now, what I would like to say, one more word before we just jump into the equations. I couldn't resist, already is there. But if you ask, what is a minimal extension of Navier-Stokes equation that allows for these antisymmetric components? Well, the answer is, well, if this is your favorite, this is, of course, convex, this has the nonlinear derivative in there. This would be the normal shear viscosity. These odd asymmetric components are the odd viscosity. Now, if you go in 3 dimensions and you start breaking isotropy, you can generate even more component. But this is the sort of most minimal model that will allow for the presence of odd viscosity. One final comment before I return to the blackboard. We've done extensive study of how odd viscosity is generated from microscopic considerations. You may ask, I know how to produce a viscosity from collision in a gas. how do I need to modify the mechanicistic rules of a collision between two particles so that the odd viscosity arises, and how that explains its emergence in this physical system? Let me say a couple of words about it. Let's imagine that you have two particles, and there are also people studying these problems in high-energy context, incidentally. My colleague Dam San being one of them. Or Paul Wigman, for example, also in quantum condensed matter. If you have a head-on collision between two particles, and you allow for the possibility that would exist if there was a little bit of friction, for example, between these two particles upon contact, that they may recoil at an angle, that simple collision operator modified by this rotation will generate odd viscosity, and we proved it. We have papers, and if you want to read a bit of a review of what's known, at least what was known to us as of 2023, this is a place you may consider. Now, how would you produce this, for example, if you spin particles in a fluid? Well, if you spin particle in a fluid, you're going to rotate the fluid around the particle, and that rotation of the fluid around the particle will generate a force on the other one. These forces are very well studied. They're called lubrication forces. And not surprisingly, because they're essentially an analog of a friction, lubricated by the fluid in between, they have a transverse component. So they will generate exactly this type of collisions. And this is at least one plausible mechanism for how odd viscosity could emerge at an effective level in a medium of such particle embedded in that fluid. So if you like, it's a hierarchical construction. There's a fluid, there's a particle embedded. The particle embedded and spinning are the fluid that has the emergent odd viscosity. Okay? So I hope that this gives you a sense that the second part of this talk, where we try to figure out the consequence of odd viscosity on turbulence, is not entirely theology, in the sense that at least the odd viscosity exists. To the best of my knowledge, however, detailed study of turbulence in three-dimensional odd viscous fluids, with the possible exception of things in plasmas that I might have overlooked, or observation that have not been quite interpreted in this slide, is still an open question, even from the experimental perspective. I would argue that even from a theoretical perspective, we're still in the infancy of understanding the phenomenology. And from the perspective of mathematical proofs, as the same friend told me in Paris, when physicists talk about proofs, is usually an oxymoron. So I'm not even going to talk about that, but I think the subject is highly mathematizable, given the state of the art that is somewhat limited. So let me, if I may, reverse to the blackboard again. What I'd like to do now is first recap for a moment the form of Navier-Stokes that we wrote there. I'm going to write it in a somewhat slightly different manner. But you'll see it's absolutely equivalent. Let's put this row here. You'll forgive me if I'm a bit cavalier in the desire of saving time sometime. So this is the terms of Navier-Stokes equation that are familiar to you guys. And if you could revert the slides to the blackboard on the side, things would be perfect. Now, this is the normal viscosity. If you take the viscosity coefficient, you divide it by density. We can call it a kinematic viscosity. Put maybe the density here. This equation has been seen before. Now, what you have to do in order to add the additional component, you want to put nu naught z, the direction in which you apply your magnetic field, cross, this is the antisymmetric structure that I was mentioning, Laplacian of V. This is the new piece. I just rewritten what was on that blackboard in this form. So this is, if you like, the definition of the problem. Study turbulence in the presence of this term. And I mean, it's pretty obvious that there is a natural ratio here between the odd viscosity and the new viscosity, and the dissipative viscosity. For simplicity, I just restricted to shear viscosity on the dissipative side. And so, evidently, different regimes will occur depending on what this ratio is and what part of the spectrum you're looking at. And so, the first thing I'd like to do is to show how you analyze or how you formulate a candidate for a scaling theory of the turbulent cascade. Well, let's start with what is perhaps more intuitive, the low-K regime. Before I move on, I would like to do an operation. You know, at least for me, it's always easier when I think of a problem that is new to me to ask, what have you seen in life that reminds you of that? I mean, not everybody likes to think of that. But so for me, when I looked at this equation, I say, okay, what's this Z cross Laplacian of V? What have you seen in life that is somewhat similar? Well, one thing I've certainly seen in life is people rotating a bucket of water. It happens, this experiment in the atmosphere every day. And that corresponds, among other things, at the very least, to adding in Navier-Stokes equation a force, which is a Coriolis force. Omega, if it spins in the Z direction, the bucket, cross V. Do you agree? Okay. So that suggests that the odd viscosity is like a wave vector dependent rotation. Why? Because if I Fourier transform this thing here, I'm going to pick up a k squared in front. So I could sort of say that if I look at this equation that is rotating, well, the term you would add for rotating turbulence, and I compare it with what I have, then I'm going to do the following. I'm going to define this new mathematical symbol, which means metaphorically equivalent. So the rotation, the rate of rotation is metaphorically equivalent to odd viscosity. Pardon, nu odd. Sometimes I get confused between eta and nu. It's just 1 divided by the density. So we can tolerate some topological stability of notation here, I hope. So this is what I'm saying. You see, just by comparing these two. The odd viscosity is a k-dependent rotation. Is this clear what I'm saying? I mean, I don't pretend that the notion of metaphorical equivalence is necessarily well defined, but you see where I'm trying to go. So, but based on the principle, on this simple observation, when k is 0, well, when low k, this term will be not being particularly important. And what I'm going to be left is what I presumably know how to deal with, or at least the state of art of what we know to know, which is in the cascade regime, Kolmogorov scaling. So
if k is small, then the normal viscous term is also small. They're the same scale, the same as k.
That's right. So it's also an implicit statement of how you take the order or limit on nu naught over nu. You see, let me put it this way. For any given nu naught, for any given finite nu naught or small nu naught, this effect will be enhanced at large k and progressively suppressed at smaller and smaller k. Okay? And one of the things that I hope to clarify in the next boards is to actually make the statement precise by telling you, okay, if there is a crossover between the two things, what is the spectral point where this happens, where is a k odd? And I'll do that in a moment. But for a moment, at the very least, you can accept the fact that if I put this coefficient eta naught to 0, then I retrieve Kolmogorov. So there is a natural perturbation theory that I can do in eta naught over eta. Okay? And when I do that, I retrieve Kolmogorov. Scaling. Now, just for the people who are asking questions, after I do the poetry on the blackboard, there will be a series of detailed simulations that show the validity of, or at least the result that we have in support of the scaling. So it's not entirely based on heuristics. There is also numerical corroboration. So what do we do now? Well, let's try to understand a little bit this problem. What would we do usually? Well, I would start writing an energy balance equation for the transport across the scale, across scales of the energy. And this is of course, a conventional affair. And this equation will include besides the diffusive component, a transfer and a forcing. Okay, this is a very conventional step in turbulence theory. So if I look at the transfer operator here, it's very interesting to study how it emerges from modes, spectral modes of the velocity field. And in particular, and I'm going to concentrate only on this term and this term now for simplicity, this term here, T, is going to be proportional. I mean, you guys are familiar with this discussion of the role of triads in setting up turbulence, so I'm going to explore it and tweak it in the light of what I'm going to be doing momentarily. We usually have this type of problem in which we have an average. I apologize, I'll first write it, and then we'll have an average over all the Fourier modes of the velocity field. Here there could be some coefficients. They can all be calculated from Navier-Stokes. And what this equation tells you is often used to understand the quasi-two-dimensionalization in the turbulent regime, where Taylor-Proudhon arguments are not guaranteed to be valid. What this is saying is that unless there is a resonant conditions between the triad, the correlation will take place because of the averaging out of this exponential in time. And so there will be no energy transfer, okay? That's why the role of the triad is so crucial. But there's another way of forbidding the decorrelation, which is to make the exponent here 0 identically. That is to say, if all omegas are 0, if there is a resonant manifold, if you like, that is another way of promoting the energy transfer. And so the first thing I would like to do now is the following. Here we have a theory, and without any ambiguity, we can diagonalize it or linearize it and study the spectrum of the theory. What is the spectrum of the waves that live in this fluid? Okay? This is an exercise that you'll forgive me if I don't do in all the details on the blackboard for reasons of time. But the answer is, it will depend on this new odd, okay? And it will be, of course, maybe not surprising to you guys, highly anisotropic. It singles out the z direction because we have a system, if you imagine that the magnetic field has been applied in the z direction, that manifestly does that. And of course, this you need a couple of lines of algebra to get it. But this is the dispersion relationship, okay?
So are you saying there are waves in turbulence because of the odd viscosity?
Yeah, that will emerge. In general, I mean, you could sort of see that this astute observation can be done from the very beginning. If you look at a matrix like this, right, you see what I mean? The first thing that comes to my mind is a symplectic structure. So you will get a generation of oscillations by virtue of this asymmetric coupling that is introduced, okay? So that's the essence. So what you're going to see is that the higher the odd viscosity coefficient, any certain spectral region, the more the generation of waves will happen. And that is what I think may be of some interest to some people in this collaboration. But let me walk slowly so that the conclusions do not appear to be entirely arbitrary. So let me box this equation. First consequence of this equation, notice that if kz equals 0, this is 0. And all of these guys are 0. That is to say, there is a resonant manifold, which is the one in which the system is quasi-two-dimensional. Okay, the kz component suppressed means that all happens in the plane perpendicular. This is quasi-two-dimensionalization. And that already in the mind of an expert on turbulence will invoke certain scenarios that can appear. But to be more precise, and to allow detailed comparison with the numerics, and hopefully in the future even experiments, let's take a look at what the spectrum is, or what we would predict this heuristic argument lead to for the spectrum. And one of my favorite, so at low k, we're going to get minus 5/3 law. It's Kolmogorov. Okay, provided the odd viscosity is sufficiently small, which is a statement of what low k means, which I'm going to clarify momentarily. But how do we proceed in the other regime at high k? Okay? And I'm going to still assume that the energy is being injected at a very large scale, so at very small k. I'm going to do it now. Now I'm going to do a different regime. Nu naught over nu much less than 1, and nu naught over nu going to infinity. the domain where the waves dominate is the nu naught over nu going to infinity. Okay, so what I'm going to do now? Well, I'm going to pull out one of my favorite the results in the theory of turbulence by Kreischten that gives the power spectrum, very beautiful and simple essential dimensionality result, which is you can express the power spectrum as a function of the energy injection rate denoted by epsilon, a characteristic time scale, times k to the minus 2. This comes truly from dimensional analysis. Okay? Now, tau k, usually meaning in Kolmogorov turbulence, as a meaning, or eddy turbulence, is the eddy turnover time. Okay? For people who are wondering whether I got the case right, remember that in Kolmogorov, scaling this, one over that is 2/3. Divided by 2 gives you 1/3, multiplied by minus 2 gives you the celebrated Kolmogorov scaling relationship. Okay? So this is Kreischten formula applied to the low k regime where the Kolmogorov scaling happens. And that is absolutely standard. Now, and that suggests this heuristic picture, which is, if you like, a perturbative argument, meaning as small k, I'm coming with the minus 5/3 law, Kolmogorov. But then, at some point, something happens. Point meaning place in the cascade. And what can happen here? Well, this eddy turnover time, at some point, will be comparable to the inverse frequency of the waves. Yeah. It's what we like to call it an arrest. A non-dissipative arrest is a sort of promotional term we are trying to push. But let's do it step by step, okay? So if this intuition that Grisha was alluding to is correct, we can simply ask what? So let's say, if you like, we're building a dominant balance argument in which there are two quantities that we compared. Inverse eddy turnover time and characteristic frequency of the odd waves. The odd waves are the ones that have this spectrum. So if I stick the eddy turnover in here, I get Kolmogorov scaling. If this is eddy, I get k to the minus 5/3, because tau over k in Kolmogorov theory is k to tau over k to the minus 1 is k over the 2/3. Okay? Did I get it right? I think so. Yeah. Now, what I'm going to do now, I'm going to use the same formula, but instead of setting for tau k the eddy turnover time, I'm going to assume that I'm on the other side, and I've entered that regime that you were asking about, where waves dominate. And so I'm going to use the same formula, but with the inverse of this. Let's just do that and see what we get. E of k, well, I mean, it's the same damn formula, so we know. It's going to be like k to the minus 2 is there. But then, now, here I'm going to do something that it's a little bit cavalier. I'm going to say kkz is k squared. You can see that here we're going to lose a little bit the nuances of the anisotropy of this phenomena. But if we do that among friends, we're going to put this guy in here. So theta is going to be, I'm just reading out from there, nu naught k 1 over this whole thing. 1 over tau is a frequency and is, oh boy, mu naught k squared. Agreed? So k squared, 1/2 is k. It's going to cancel one of the k, and you're going to be left with eta, the nu naught, inside the 1/2 here, and this k will be -1. You see what I've done? Okay? So this is the power spectrum that I would obtain in Kreischian formula if my hypothesis was that the dominant time scale was the inverse frequencies of those waves. And now, one question that I can ask is, at what k, this is related to your point, at what k, a k that I'm going to call k odd, does the tau eddy becomes comparable to 1 over omega odd waves? Okay? That's going to be the point in the spectrum where I'm going to presumably cross over from the -5/3 law to the k to the -1 law that I just derived. Assuming isotrope, which is not a good thing, and if you read our papers, we've been a little bit less cavalier about that. But as a first pass, allow me to proceed. Okay, now, if you make a more detailed analysis for the anisotropy, there's a second length scale at image. But let me at least do this. So what are we going to do here? Well, again, how do I get k odd? I match this to this. Okay, and my objective is to understand how does this k odd scales with the odd viscosity. Okay, so what I'm going to do, I can either match these two, and let's do it like that. So I'm gonna write this. It's equivalent. Okay, so this is k odd to the 2/3 is this inverse time. Okay, and I'm gonna balance that with this omega naught k to the power of 2, okay, odd. Because, odd is the inverse length scale where these two things are matching. Do you see what I'm trying to do? And that's why I put that label in there. Okay, so, well, then here I just have to do, difference between two numbers that even on a blackboard under pressure one should be able to do, which is 6/3 minus 2/3, it's 4/3. So that means that, remember the one is upside down, but I think that this is the result that we would, and nu O, I'm putting these O's all over the place, but wherever you see an O is the odd viscosity. Okay, so odd is the same.
It's almost viscous scale
Yeah. But with a non-dissipative coefficient, which is quite important. Okay. But let's continue now our discussion. What do we want to say? So this one now has given a slightly enhanced picture, right? Is saying, if all of this scaling is correct, and when I'm going to show you the numerics, I'm going to show you that it is actually quite useful to, instead of plotting the power spectrum, plot the power spectrum divided by the Kolmogorov spectrum. Because you see, like your idea is to see the deviation from Kolmogorov spectrum that arises due to odd viscosity in different portion of the OK space. Okay? So if I do EK divided by Kolmogorov, and I don't want to write Kolmogorov, so I'm going to write D, then at very small k, I'm just going to be 1. 1 means the -5/3 law, okay? But then I'm going to eat later, if I do a good job. Hit a k called k odd, whose dependence on omega I calculated for, or I estimated for you here. And then I will enter this regime of k to the -1. This k to the minus 1, if I divide by k to the 5/3, which is the Kolmogorov scaling here, will be something that goes up with a k to the 2/3 power. Can you see what I've done? So this is the wave-dominated regime, or starts being the wave-dominated regime. This is, if you like, the regime dominated by eddies. Okay? But you sort of can imagine that at some point, this flux of energy that is coming down will be arrested. This is what Grisha was trying to guess. And so this thing cannot go up forever. It's got to come down. So there's going to be a second frequency, Kc, not free, well, wave vector Kc, that also will depend on odd viscosity in a certain way that we can estimate as well. So let's summarize all our conclusion. Here we said this is mu naught to the minus 3/4. What about this other guy? How does it scale? Well, let's return to the fundamental equation of turbulence, or simply the balance transfer equation applied in the cascade. Let's go back to this equation and integrate it. So what we're going to say is the following. Again, heuristic argument. We want all the energy that I've been injecting, start integrating. So let me just write it down and then I talk, so otherwise it's a bit of a... You see what I'm doing? I'm actually integrating the dissipative term, that is the one that is going to absorb the energy, over all k's. But what k's matter? Well, let's imagine that I come here, from here. If I'm in this part, the one that you're dominated by the eddies, then dissipation is not an important thing there. It's only from k odd to kc, when the sharp downfall occurs, that integral needs to be evaluated particularly carefully. So I'm going to write here that the domain of integration is k odd to kc. And what is kc is the characteristic portion in k space, the characteristic place in k space, where the energy is the power spectrum is peaking. Okay? So let's try to now estimate this quantity. Again, at the same level of dimensional analysis that we've done up to now. Is a question? Please. Maybe can you switch on the machine so that everybody hears you?
Can you use the microphone, please?
In your computation of k odd, you match it kz with k squared, right?
This one here.
Yeah. Is that reasonable, or?
Say again?
You match it kz with k squared, correct?
Yeah.
So is that, what's the point then of having this anisotropy?
Well, the anisotropy, I hear your point. What you're saying is that I thought that odd viscosity was generated by anisotropy in the first place. The answer is no. Anisotropy is an accident of 3 dimensions. Let me walk with you. If you look at those equations and you ask what symmetries you necessarily have to break, the answer is only 2, parity and time reversal symmetry. Consider, to understand this statement, the case of 2 dimension. Okay? Now, in 2 dimension, you have all the particles in the plane. They all spin like that. There is an omega that is going out of the plane. So you can be completely isotropic in the plane, but you still generate these effects. A little catch is that this effect a boundary effect. So do you see what I'm saying? Like, odd viscosity does not depend on the fact that you break isotropy. It relies on breaking parity and time reversal symmetry. However, when you want to do it in 3 dimensions, well, your field of spinning is embedded in the space in which you live. So the 2 things are intertwined. And if you did a rigorous analysis of this problem, to some extent we even did it, you will find slight nuances on this argument that arises from that. But it does not miss anything crucial, because the crucial thing is not anisotropy, is the other two characteristics, is the chirality. This is a chiral symmetry breaking fluid. Now, let me estimate this. This is also quite simple. Why? Because since we are restricted to this regime, because here you have a lot of, you don't have dissipation, we know what the spectrum here is. If you work in natural unit, it's k to the minus 1. So you're going to have essentially k to the minus 1, and there is all the other stuff, okay? K squared. And from the perspective of, this guy here is k to the minus 1, but there is also a dependence on nu naught. There's also epsilon nu naught to the power of 1/2. Can you see? I just copied that. And so what I have to do now, I have to do this integral. And I'm going to do this integral by dimensional analysis. So the dk yields the k minus 1. And the only thing left is the k squared that is nu naught. So what I get out of dimensional analysis is actually epsilon. Yeah, the nu, we don't care. K squared. C. I'm going to assume kc much greater than k odd. So k odd, I can take it to be a very small number and neglect it. So I can then only evaluate this expression at the upper level of the integral, kc. So I get nu kc squared times epsilon nu naught to the 1/2. And this allows me to conclude that kc is proportional to nu naught to the minus 1/4. Can you see that?
Wave number where isotropy breaks?
Yes, it so happens. It so happens. I don't think that based on what I've shown, I can say that. And you can also see it from the pictures. Oh, okay, well, whoever said it is not wrong. So even if it was wrong, you should be encouraged to, to interrupt. And so here there is now, let me just recap. There is a second key characteristic Kc. Okay? Please.
That okay, the dispersion relation is like Whistler waves in plasmas. And what you're doing in the spectrum dimensional analysis is like equivalent of Eroshnikov-Kraichnan spectrum.
Absolute.
And so, and that also suggests that what you have in the at high k when over a crossover is going to be wave turbulence, three-wave process of wave turbulence of Whistler waves.
So one of the things. Yeah. So one actually, there's one of, I roughly gave this presentation in Paris a few months ago, and then I met Sébastien, and we had a lovely afternoon there in the woods at École Polytechnique, and we discussed extensively this. And since then, we've been doing simulations that target, in particular, the IK regime, the one that are reported in the paper that I wrote here at suboptimal. And we've been studying also what happens when you pump energy at k is larger than k odd to study the direction of the cascade. And your guesses seems to be backed up by preliminary evidence, but I don't think we can yet say for sure. But we do see hints of wave turbulence precisely in the regime where you, and I'm going to show you there's also signature on the behavior of intermittency that strongly back up that conclusion. And this is one of the directions where attempted mathematization would be very invaluable. And Sébastien, I don't know if you want to add anything about that, but I think that there is preliminary evidence of that wave. Wouldn't you agree? At least from simulation, and they are consistent with wave turbulence calculations. Okay, but here already on this blackboard, I showed you a bunch of stuff that did require a little bit of believing. So one thing that would be nice is to see, okay, how much do direct Navier-Stokes simulation show of the phenomenology that has been delineated using scaling on this blackboard. And so if you like, let's just make a summary so that in our mind we're all on the same board, is that we're going to have a low K, a net turbulence regime, where it's going to be Kolmogorov. So if we make this plot and divide it by the spectrum of Kolmogorov, it's going to be looking flat. Then we're gonna cross over to the k to the minus 1 regime, that once you divide the k to the minus 1 by Kolmogorov, looks like k to the thirds. And then it's going to go down the curve. And the place where the onset of the wave-dominated regime occurs happens at this characteristic wave vector, and the maximum happens at another wave vector. And so what we can do is we can do Navier-Stokes, what's my collaborator Xander De Witt, a very talented postdoc supervised by Federico Toschi, did, is to carry out extensive simulation for increasing number of nu naught, more precisely the ratio between nu naught and nu. Okay, and this is what I want to show you. May I have the slides, please? Yeah, I will do it, don't worry. Okay, so the first thing that I quite like, and of course these guys are my collaborators, that you can see their picture there. So just at a snapshot, because it's actually quite fun to look at pictures, especially after an avalanche of estimates on the blackboard, is that what this is a cube for a fluid with no odd viscosity. So this is how by eye Kolmogorov spectrum looks like. This is the vorticity that is being plotted here. And this is what an odd fluid is. And please notice that by odd fluid, I mean a fluid with a large value of the odd viscosity. Even by eye, I would venture to say, if you compare a snapshot of this projection, no odd viscosity and odd viscosity, I would say that you start seeing hints of I would say, a wavelength selection occurring. Maybe one could even use the word pattern formation. Okay? But of course, the way to do it properly is indeed to measure the power spectrum. And that's what we did. And now here, it's quite interesting to compare this to the, no. I'm going to flash it in and out. This to this. Also because the numerics never look exactly like. So this is the eddy regime. This is what you see here. Okay. Then there is a peak of the power spectrum. That's where the pattern is more pronounced. And what you can do is you can see that the peak is shifting depending on the value of odd viscosity. Okay. Say again? Yes. Yes. So this thing here, the odd viscosity, the green one is the most green one is the largest value of the odd viscosity. If you look at the position of this peak and you measure it against the eta odd, which is the odd viscous coefficient, it's not many decades, but this is nu naught to the minus 1/4. Yeah, I'm going to show you that too in a moment. But first, remember this. Our estimate for Kc. Backed up here. Second thing you can do is precisely what was suggested. You see, what we said is that the crossover from flat to this regime, what we call K odd, should scale like nu naught to the minus 3/4. So if you rescale all the K's in that plot numerically, you should have a collapse of all those curves to the same starting point. And that's what I'm going to show you momentarily now. I've done the same plot, but I divided by K over K odd. Notice that almost all the curves start piling up. This is the K to the 2/3 that we predicted. And if you like, this to my eyes is, a semi-validation that the scaling argument is not completely off. Now, I see that time is running, so I'm going to just put one line of advertisement. I mean, maybe this audience doesn't need to be reminded what anomalous scaling and intermittency means. The only thing I want to tell you is that, and that goes also a bit in the direction of your comments. We have studied in a recent paper, including also Han Shen and the gang from before, the behavior of intermittency as you increase odd viscosity. And what I want to draw your attention here is that as you increase the value of the odd viscosity, you have a convergence towards Gaussianity. That is another think piece that perhaps goes in the direction of this connection to wave turbulence. And perhaps I hope that maybe next year you can invite Sebastian, and he's going to give you a full theory that hopefully we will develop to build upon this heuristic understanding. Thank you very much for your attention, and sorry for going over time.